Okay, section 8.8, Taylor and Maclaurin series. Now in previous sections we saw that we could define a function that's equal to a power series, and this is an infinite series from n is equal to 0, say, to infinity for something like a in x minus a. And so here we have a series of coordinates that are going to be multiplied by this term, actually raised to the nth power. And so we're centered at little a, and we have these coordinates. And we decided that, that's a function. Now with the Taylor series, what we're going to do is modify this a little bit and say, well, what if instead of coming up with this and calling it a function, what if we just had a function already and wanted to ask the question, can we formulate this function in terms of a power series? So for instance, just as an example, you've seen this in class, e to the x, well that's a function. Can we create some kind of a power function for this thing? Where we've got, and if we only knew what values to plug in here, we could have a way of calculating e to the x, or cosine x, or whatever. And that's what the Taylor series is. To actually answer the question, can we do it for a particular function, we have to wait till next section. But we can look at this problem right now and see how would we go about building a Taylor series. So our next question is, if we think we can do this, how do we go about determining what these coefficients are? So let's now, instead of using a specific example, let's make it generic again, and we'll just say we have some function of interest, f of x, and we would like to be able to write this series, this power series for it. Well, f of x, and let's just keep it abstract now, is a0 plus a1 times x minus a plus a2. This is just developing a power series, right? X minus a squared plus a3 x minus a cubed dot dot dot. Okay, so far so good. Now, we've learned in the last section that we could differentiate this. So let's do it. We'll differentiate this. This is our true function, like it's e to the x or cosine, whatever it is. And now we're going to be dealing in the abstract again. We don't know what these coordinates are, but we can still play with them. Well, this is just a constant, so that's going to come out to be 0. So then we get a1 times 1. This is a constant, so that goes away. So we just get a1 plus a2 times 2 times x minus a plus, well, there, maybe I'd better bring that 3 out in front. I was a little sloppy before. X minus a squared dot dot dot. And f double prime, take the second derivative, is equal to, well, this becomes 0. So now this we get 2a2. This is 1 now, so that's plus, now we have to bring the 2 down. We get 2 times 3 times x minus a dot dot dot. And we could keep going on this way. And how is that helping us? We're getting all these terms, but we still have a whole bunch of unknowns. Okay, let's not get ahead of ourselves here. How are we going to figure out what these coefficients are going to be? Well, we assume that whatever function we have, it's going to be differentiable, so we can get out these derivatives. And now we can pretty easily write an equation that's going to solve for what these coefficients are. Let's just take this example right here. How are we going to do this? Well, we're going to have to make an assumption And what we're going to say is that at the point where x is equal to a, that's a perfectly valid point, we can do that. We are going to be able to look at this and say, well, look, when x is equal to a, x minus a is equal to 0, and this term drops out, and this term drops out, and all terms after this drop out. Therefore, f of a, because x is equal to a, f of a or f of x here, where x equals a, that's a kind of a special case there, is equal to a sub 0. F prime of a or x, whatever we want to call it, is equal to, now when we've taken our derivative, of course this dropped out, all other terms besides a1 includes 0 term, therefore they drop out. And then we get down here and we see f double prime is equal to 2 times a. And what happens is then we can solve for these. For instance, let's solve for a2. Maybe that's a 2a. That's maybe a 2a sub 2. And what we do is we just have to bring this 2 over and we get f double prime of x, which we can calculate, divided by 2, is equal to the a sub 2 coefficient. And in fact, in general, we can come up with an equation for this, and you can look at your book and convince yourself that the nth coefficient is equal to the nth derivative of, and let's just might as well write it as a, okay, divided by n factorial. And the n factorial comes from the fact that as we differentiate this power series, we can think of this really as 1 times 2 times 3, and the next one's going to have a coefficient 1 times 2 times 3 times 4, etc. That's where this n factorial comes. And as soon as we have this, and the ability to differentiate infinitely on our function, then we can come up with as many coefficients as we want or need. And that's basically then how we're going to construct this Taylor series. We differentiate, we're going to be dividing by these factorials, and we're coming up with these coefficients. Okay, we can use these coefficients to come up with a general form for our equation, for our Taylor series, and we're going to write this as, let's pick a variable that's used in the book. K is equal to 0 to infinity, and our generic representation is the kth derivative at a, where our Taylor series is centered at a, divided by k factorial, times x minus a raised to the k power. So what we're doing with this is trying to estimate our function at some x value away from our centered value of a. The Maclaurin series is similar to this, except by definition it's centered at 0. So if we were to rewrite this, and then just every place that we see an a, we just substitute in a 0, what we get is still the kth, but now at 0, and divide it by k factorial, times, now it's x minus a, but a is 0, so we just get x to the kth power. Okay, and that's its series. And if you look on page 554, it's got a definition box that shows you all this calculation.